the case of that we see in the video of the water being liquid, but it was in a sort of metastable state, and all of a sudden it got solid. So you have these two phases, X and Y, no? So you're representing, for instance, the situation of liquid phase or solid. And but you are in conditions that it should it should go from X to Y. The conditions of that water were such that should be solid. But instead of that, instead of going from X to Y, it stays in a sort of state that looks very much as X. It's not an equilibrium state, but it looks very much as X, that I'm writing as X prime. No. And some small fluctuation might trigger this quick transition to Y, as we saw in the video, exactly that. So it's very many common classical examples like supercooled liquids that we were talking, the same as between vapor and liquid, supersaturated vapors. Also in ferromagnets with the magnetization opposed to the field. That's something we study in the school, this hysteresis loop. And this is somehow the main example that I want to talk today at the end of the, from a mathematical side. So you, here in this picture, you represent here magnetic field and here the magnetization, say. You are in a situation, say your magnet is negatively magnetized, so you come with a negative field and it stays negatively magnetized. Then you make this field smaller in modulus, that means closer to zero. The magnetization gets a little bit smaller, but still is negative, a little bit bigger, say, but still negative. And then the field is zero. It's even positive, and it still keeps a negative magnetization. Then at some point, there is a sort of coercive field that it will make a transition to plus magnetization, and it the other way around. And how big it must be this coercive field depends on the material. There are some materials where it needs to be big, others small. But this is the so-called hysteresis loop that we know a lot about it. So I already mentioned these two properties. This X prime is not really an equilibrium state. And then a small perturbation makes it go to the right phase, which in that picture was Y. And usually there is some critical droplet, as we see in the bottle. There is some small droplet, and we'll see in other examples. So it is truly a phenomenon of non-equilibrium, not of the system. And there are some questions that we want to address usually, which is what does it mean, this, what people say, metastable branch? No, and from dynamical side, one important question is the lifetime. How long does a metastable state last? This, because sometimes the metastable state is very important because it is applied. It is something to be used. Many. Okay. I like very much this quotation of Gaveau and Schumann, which is this the gentlest of non-equilibrium phenomena, but it is a non-equilibrium phenomenon. And in terms of applications or where you see there is a huge variety. Physics, you know, these nanostructures, you have plenty of metastable states. In biology, I just put a picture from the web, which is some proteins, which is in materials, because many times it's very important to have some alloys which are metastable, and they are important for the applications. In economy, maybe some bubbles which are metastable. study of climate. So it's frequent, you find examples everywhere. And going to a mathematical or a physical, theoretical description, I think the first description was given by Van der Waals and Maxwell, and has to do with the vapor-liquid transition. In that video, we have a liquid solid, but here is about the vapor-liquid transition. And what was it? It's a sort of semi-phenomenological argument, not really. This was so early times of statistical mechanics. So Van der Waals started by this perfect gas equation. So this pressure, this is V, so-called specific volume. It's 1 over the density. And this is K is a constant, Boltzmann constant, and T is the temperature. So this is so-called equation of a perfect gas. So what out of this equation, he says, well, let me improve it a bit by considering that there is the particle, the molecule is not a point, it has some volume. So I consider that it has some volume that's called B. Then instead of keeping B, I should keep V minus B, because this is the available volume. For each N is the number of particles. If I'm thinking V is the volume divided by the number of particles, so this is the total volume. So at the end, it gets this. And let us put this term here, A divided by V squared, to take into account some attractive at the long range, the things at far distance they should attract. Then you get this equation for maybe, well, and you just draw the curves PV for each fixed value of T. Then, of course, it's very simple. You realize that there is a T critical, which is this one, at which your curve will have an inflection point. And for T smaller than that, you have this behavior here. There is an interval where it has something very strange, because in this interval, what you see, V is increasing. That means density is decreasing and the pressure is increasing. It doesn't make sense from any physical point of view. No, something is wrong, because it cannot be the density is decreasing and the pressure is increasing. No, doesn't make sense. So something is wrong, and this is not the case, cannot be the case. So Maxwell found a correction. What should be the correct thing? He just puts the correction should be that in this part, there is an interval here of V for which this should be constant. Pressure should be constant. This material substance is not homogeneous, and this pressure is constant. And then you ask, but where is this line? And he said, well, the correct place to put it is at the point where the two areas below and above this line are equal. This has an argument which is partially justified by thermodynamics. So that was Maxwell. There is no statistical mechanics here. It's just phenomenological and mixed with semi, because of some arguments based on thermodynamics. It's a nice argument that he found. But there is another thing in that picture that immediately one sees. Well, that part was not good, but there are two pieces which still make sense. That's this piece here and also this piece here. Here from vapor to liquid and from liquid to vapor. And what are their meaning? So they are somehow, they thought, this is the thing which is connected with metastability. Okay, so this theory, that's why it's called Van der Waals Maxwell, because it was includes the correction of Maxwell. There is a place where it is very nice to read about all Van der Waals lab and so on, It's a book called How Do Fluids Unmix? No, it's not about so much about the the arguments, but all the construction, the lab, how it was. It's very curious, very nice. I like. So there are these two problems which emerge out of this example. Now that first, a more rigorous justification for this Maxwell rule, and there is another problem which is connected to this, that this was treated as if it were a situation of equilibrium, but it's not. So one needs to understand if it's not equilibrium, better we look at it from a dynamical point of view. That was, and progress on this, how to justify, how to put Maxwell rule within statistical mechanics. This was done in the 60s of the 20th century by Lebowitz-Penrose, but it was initiated by the work of Katz, so it's the Katz potential. And I didn't call it's a paper of Katz, Uhlenbeck, and Hammer, but we are not going to discuss. So just to say, there is a way to see the Maxwell rule as a rigorous result in statistical mechanics. It emerges when you take, because why you have this strange thing? Because you are treating as homogeneous something which is not homogeneous. You are treating as if the interaction were the same from in each two guys. And so what the Katz potential do is exactly that. Take first some interaction within a given, which is somehow constant over a very long range, but these are rescaled afterwards. So I don't want to enter this today because our goal is another one. But there is a way, and this was done through the Katz potential, to connect this stuff, which is semi-phenomenological, with statistical mechanics. And these branches, the metastable branch that we see, it is really a peculiarity of mean field, of this kind of interact with everybody in the same way. So, and this is also mathematically treated in a particular case by Isakov first, and then there is a paper by Sasha Friedel and Charles Pfister, which deals with that. But we are not discussing that, just to mention. And what we are focusing mostly is this. This is, since it's not a problem in equilibrium, we should look at in a dynamical manner. And indeed, Maxwell already comments on this importance of nucleation, how this droplet nucleates, and so dynamic aspects. And there is a theory on that. I mean, this mathematically trying to do this micro, this description was in the 30s. So now let's go, since I'm more focusing on the math. So let us go for this dynamical treatment. So these early days of looking at it in a dynamical manner. So it is clearly Arrhenius law that comes up. And so this is, you want to see what is the, so this is the so-called chemical reaction rate theory. And there are two names important here that I'm sure there are others, but these are the two that emerge more prominent, Van Hoff and Arrhenius. So you have this classical Arrhenius law, which is R is the reaction, the rate of reaction. So 1 over R we think as the average reaction time. And here it is, so R decays exponentially in the energy divided by the temperature with the K. That's kind of, one part is the energy, the other is the entropy, the temperature. So if we think of the time to happen this reaction, then it will be growing exponentially in the energy. But it takes into account the entropy as well. So there's this law, but this is just not mathematics. So in order to develop some mathematics that was to prove Arrhenius law, and probability comes in, but we are already thinking of something which is, whenever we put in Brownian motion, is already not a microscopic, it's mesoscopic. There is a different scale. So there is very important to work of A.N. Kramers, which can be understood as a first derivation of Arrhenius law in mathematics. So you have a simple model for reaction diffusion where you have large viscosity. That means the diffusion is very small. So it is just an Ito equation in our terms nowadays. So this dx is minus u prime. So u is a potential. And here you have noise, stochastic noise, which is epsilon dB. So it's a Ito equation given by that. So this u, in order to represent a situation where I have a change of two states, to phase, u is a double well potential. So there are two minima of u, two local minima. Okay, so you think of a paradigm of this as so this is our u. This is the potential, so the force is the derivative minus the derivative of this. So it has these two minima. So somehow your x will be not really like this drawing, but it will be trapped for a while in one well. After a long time, it managed to escape to the other one. And if the other one is deeper, then it will take even longer time to come back, but it will. So, and then what Kramers prove is that the expected time to go from, say, the neighborhood of A to the other side, it is of this form. So it's exponentially in the difference between u of the local maximum, that's the barrier that you have to overcome, divided by epsilon squared. So it's a mathematical proof of that formula of Arrhenius law in some sense. Okay? But it's not at the microscopic level. It's already a stochastic process that you take like that. So there were many developments in this, because this already goes into the frame of small random perturbations of a deterministic dynamical system that are connected to that, all the Friday and Wenzel theory. And there are important works in infinite dimension with SPDs. And I just quote one of the first here, which is paper by Fares and Iona Lazinho. And what happens is that in the value of the, I didn't write here, but I should have written somewhere, the value of the prefactor k here is in the particular case of one dimension, it is obtained, but that's a very particular case because of my Kramers. And in more general situations, in order to obtain a good control of K, usually it's important to take potential theoretical tools into account, and this has been done by certain group of authors that I call some here. So there is a good development in this direction. But as I said, this is a kind of mesoscopic system. And looking at statistical mechanics, which tries to make the connection between micro and macro, still something has to be done in a different, starting from a microscopic dynamics. So, and an important role in this is played by Leibovitz and Perros.
So, can I ask you a question?
Sure.
So if you have, let's have two complete graphs connected by just one edge, then if you do a random walk, start a random walk at one point, it will take a long time to get the other one. So can you put?
Yeah, it can be.
So that's
it can be put.
Description, right?
Yeah, it can be put in that. Yeah, there are many. I will come to some microscopic stochastic dynamics, which that. But so for the moment I am doing more like how this thing developed in the theory. But this is true. It will appear something which is similar somehow to that. So what they were interested to say, can we give a description on how to put in metastable state within statistical mechanics? That's what they thought. And okay, if so, let us say there is some measure mu that is called the Gibbs measure that describes the equilibrium of my system. I don't want to get into details now on what it is, but let us say there is a probability measure which is called the Gibbs measure that is corresponding to equilibrium situation of my system. Is there a way that we might end up with some prescription for a metastable state? So their proposal was the following. They came with, let us consider the measure condition to stay within a certain region. So it's a restriction of the equilibrium measure. Thinking of that. That was the proposal of Leibovitz and Perros. So there is some R subset of the whole space, and you want to describe what properties R should have in order to say that this has to do with metastability. So they consider the three properties. There is only one thermodynamic phase. There is no liquid solid, only one. And the lifetime is large. That means if the system dynamics, say classical dynamics, starts in R, it will take a long time to exit. And once it exits from R, it will take much longer to return, as if we had these two wells. And they applied this to discuss the vapor-liquid transition in the case of the Katz potential. And this was also done in stochastic dynamics for the Ising model by Capocaccia, Cassandra Oliveri, still in the 70s. So the basic message of this kind of prescription is you have equilibrium states restricted to certain small subsets for which you see a bottleneck effect. Once the bottleneck, once it goes out, it will be very difficult to come back. It's much easier to. It's very difficult. That was, and I want to make, before I get to our model, there are a class of models that I want to make a few comments about this. So there is this condition which says that there must be large lifetime. So this is naturally, if you are thinking of an ergodic system, it's a small measure because in equilibrium, the time to get back will be 1 over the measure. So that's one possibility. In order to verify this, so I'm sorry because maybe you, what I call trees, that once it has escaped, the return is longer. In order to verify that, it is usually, and as in their case, reversibility plays an important role. Reversibility is what we have in a stochastic process, that if it's in equilibrium, you change the direction of time, and it's the same distribution. Finally, the other condition is taking the mu has to be small. This is what that was a proposal in 7. And there are other, since then, other candidates sort of general emerged, and natural things that you can imagine are the quasi-stationary measures, which have a well defined and have been studied. Also, conditional ergodicity is an important thing. This has been exploited by many people. I just put 2 papers called 2 works here, which I think are very inspiring. Laurent Miclot and Alessandra Bianchi and Alex Godelier. They exploited these ideas, and also it's the connection to the spectral properties of the generator of the process. So there has been this way to see it. So what I'm going to do is something sort of more basic, more kind of intuitive, without too much theory. That's what we kind of propose. Well, if we just think of dynamics, you see this phenomenon as purely a dynamical thing, and you want to characterize the 2 ingredients that seem clearly crucial are there is something which is called thermalization. That means that you time to reach this situation. And another scale of time is the lifetime of this metastable state. And you would characterize metastability, imagining that there are 2 scales, a much smaller, shorter scale in which the system thermalizes, but that state which it goes, it's not truly equilibrium, but it stays there for a very long time, and then it moves to equilibrium. So there are these 2 ingredients. You have different time scales, and it goes very quickly to a sort of fake equilibrium, and then it takes a long time to really converge to equilibrium. So we want just these 2 ideas, which I think all these things have this in the middle. And we want to say, let us describe systems. Can we make theorems? Can we check this into a class of systems that we sort of make a more rigorous description of the phenomenon? So having in mind these 2 elements, that the thermalization scale is much shorter than the lifetime scale. That's the main message. So it's a sort of more, maybe in some sense more general, and it doesn't matter if we are talking about a mesoscopic state, a system, it's just mathematics. So we came out with this idea. So there is this system, X represents my process, my system. Let us think it's a Markov process, but might not be exactly. And it's on a certain state space X. In order to make this rigorous, that I'm saying, thermalization is much smaller than the lifetime, I take my system with a parameter. This parameter might represent a restriction or some very small scale. So just to formulate it as a limit theorem. In practice, it's not a limit, but that's for some value of this parameter sufficiently large or small, depending on the case. So instead of having one process, I have a family of processes. But you think of this xn, n is a restriction of x to a certain subset or something like that. It will be clear on the examples. On this space X, you have 2 probability measures. One that I call mu metastable, and mu ec, which is equilibrium. There are 2 measures. And I find two scales, two time scales, theta n and gamma n, theta n being much smaller than gamma n. They are both going to infinity, but theta n is much shorter than gamma n. And I look at what one does in statistics and probability, an empirical measure, empirical process. So I evaluate how much, what's the proportion of time between theta and theta, between t and t plus theta n, that my process is in a certain subset. So just the empirical, if it were discrete time, would be the moving average. But so I just look in the window of time, t up to t plus theta n, and I see the empirical measure. So this is the empirical process. And what we want to say is that for t very close to this transition, it stays quiet. So you have a sort of a jump process. So this stays here and then it goes there. And this transition is very short. That's what we want. So it's basically saying this process converts to a jump process, Markov jump process. So it has this eta, it's very close to these metastable states up to tau n essentially, and this very close to the other measure after tau n, and tau n, which is this would represent the transition time in the scale theta n. Tau n divided by gamma n goes to an exponential distribution. That means this transition is sort of unpredictable in this case. So the exponential is the distribution with no memory. So that was what we proposed. This was back in '84, and since then, this has been developed by several authors in several directions, but it has been a kind of reasonable proposal, and we call it the pathwise approach because it looks at the trajectories of the process, be this process one type or another. And there are many examples. There are toy examples, which are very simple to deal with, like birth and death chains used suitably. The so-called Kurzweil stochastic chains, which is some simple model called mean field theory. There are also these other examples like that I mentioned before. Now all these small random perturbation of a dynamical system whose drift has many some attractive sets, a finite number of them. So this is the Friedel-Wenzel regime. And another important example, which is when you have this models, so-called the contact process, an important model for the spread of an infection. So this is a process that the infection can stay forever, like you have an endemic situation, depending on the value of the parameter. And the point is that when you restrict it to a finite set, then there is no way it will stay forever. But nevertheless, it will keep this behavior like this kind of, if you look at time average, it looks as if it were in equilibrium because the volume is very large. So you look at a finite set, you don't know that it's going to die because it looks like very close to the equilibrium. So there are many examples. So the one that I want to focus is the Ising model. That's because it has to do with this hysteresis that I mentioned in the beginning. So what is this Ising model? I'm taking dimension 2 here. So you think that each vertex of your Z2, your graph, you have a graph Z2 is the usual nearest neighbor bond. You have at each vertex, you have a small magnet, which could have two orientations, plus or minus. So my configurations are the set of plus or minus one configurations indexed by Z2. On this set, now think that we take a finite piece of this and we have an interaction when I restrict to this finite piece, which is the following. I favor, they like to be like the neighbors. So I lower the energy if the two neighbors are the contribution of this pair. I just look at pairs, nearest neighbor. These are the same sign, because if the two have the same sign, this gives a minus. Oh, here is a plus, and so I have a minus. So it lowers the energy. So it's an energy that wants them to be alike with the neighbors. Then I have an energy with an age. That is, I have a magnetic field of acting on everybody, so they like to have the same sign as each. And this is in a finite box. And then I look the outside. The outside is frozen, say, eta, and I interact with the outside. But think that the outside is an external boundary, like a heat bath, and I look at things, the volume lambda, and the eta is fixed. So you have a measure which is called the finite volume Gibbs measure, which is e to the minus beta h normalized to be a probability, where beta here is as before, 1 over beta is the temperature. So this is the finite volume Gibbs measure. And one wants to study this process because this is a simple model for magnetization. So that's the importance of this model. It's, I think, one of the models that has more papers, more work, more citations. It's the easy model. And it was indeed proposed by Lenz, who was the advisor of Ising in 1925 for his thesis. But Ising studied the case dimension 1, and in dimension 1 there is no phase transition, of course, because it's a Markov chain. And then they thought this is not going to be interesting, no? But he left to do other things. But and Piers is the one that notes the came out with a good argument that shows that this model is interesting. And since then, a lot has been done. Famous paper by Hager in 44 and Young Lee in 52, and an explosion of things. So this model is interesting. Why? Because it's very simple, and it has a rich structure as the volume grows. And what does it mean, this rich structure? It has a phase transition, like other examples that we saw, in the sense that there is a critical value of the temperature such that below this critical value, that means there is a beta critical, that for beta larger than beta critical, there are multiple limiting measures, depending on what you put on the boundary. So here I just show simulations by Vincent Beffarad. Here temperature is very large, and you see he has, I don't know if it's possible to see, there is a color black here, that means a plus or a minus, doesn't matter, and the other color this side. But you look at the, it doesn't see any difference because temperature is very large, beta is very small, so what counts is the entropy. It's like a product measure. But if beta is larger, this dependence on the outside will remain forever, in the sense that when you take the limit, it will give what you see at the origin will be positive if outside is positive, and will be negative if the outside is negative. This phase transition can also be felt through a magnetic field that is coming to zero but positive, or coming to zero but negative. And that's like as in the hysteresis group. So this was beta very small, that means high temperature. As you lower the temperature, you see that things get very different. And that's the phase transition. So because of that, this model is interesting. Well, we are dealing with dynamics. So we need to have a dynamics for this model. Well, the dynamics is something as with Friedman Wenzel theory, something that it doesn't exist in nature, we invent. No, with stochastic dynamics, we invent to play with the stochastic process. So we invent, just take an evolution that preserves, keeps Gibbs measures of this easy model, as invariant. So this is a simple one. You have many of them. So I just, what is this dynamics? It's just something which you give the rate at which you flip a spin at x, depending on the whole configuration. Simplest one, when you make it, say you flip at x or not, depending on what you see on the neighbors. So there is a very simple one, that's the simplest one. You compute the difference in energy of the current configuration, and if you flip. And if you flip, the energy is smaller, that means this plus is zero, the maximum between that. If this is zero, then you flip. You flip with rate 1. And if it is going to increase the energy, then you flip with a very small rate, because it will be, well, you think here better. So you flip with this rate. Why I choose that? Just to have that this is a stationary measure, not only stationary, but reversible. You have this condition verified. This is well-known dynamics used a lot in all sorts of algorithms. When you want to simulate a measure and you start from something and you just use some stochastic algorithm, and you at some moment you stop and say, here is my realization of the measure. That's what you do. One needs to be careful, because if this has metastability, maybe you are not really in the good way. You are in a well which is not the deeper one. But anyway, so that's this kind of dynamics. Okay, for instance, we might think of the metropolis. That's the simplest one. So if a flip will increase the energy, then it flips with rate e to the minus beta times the difference. If it will decrease the energy, then it flips with rate 1. Okay, that's just to have a stochastic process. But it's not unique. There are many that you can choose, and there are many results about metastable behavior along the pathwise approach and various approaches for this kind of dynamics. When you are in the regime that beta is going to infinite, that means temperature is going to 0, things are frozen, and the age is fixed. And there I just wrote a list of people who have papers on that. And as you see, if the volume is fixed, this corresponds to the setup of Friedel and Wenzel, so-called chains in the Friedel and Wenzel regime. That means the probability transition from state I to state J it will be of this form. That means there are many sets where it flips with a rate which is not too small, and there are some which the rate is very small, like in the example that you were saying. So there are this so-called Friedel-Wenzel regime. These are an ingredient part in the proof in the book of Friedel and Wenzel, for instance. In order to study the small random perturbation of a continuous system, they need to study chains of this. So there are many tools like large deviations, renormalization, potential theoretical tools, and you need to understand how is this energy landscape and try to find the best of what you can do. So there is a lot of that. And looking at a particular easy model, so this landscape might be complicated because you have a set of 2 to the volume of delta configurations. But an important thing on that for that to see how it was not clear that this would be a chain in the Friedel-Wenzel regime, and one would be able to see. The key thing was this paper by Neves and Schoman. They look at dimension 2, so the volume is fixed. Beta is going to infinity. That means these rates are when they are small, they are pretty small, and there are some which are rate 1. So there is a very, very drastic change, and you need to find out this the one where you are going to the highest barrier that you need to cross in order to go, say, from minus to plus, thinking that the magnetic field is positive. And they figure out what it is. There is a critical size, which depends on the age. Age is fixed, and you know that this is the barrier you have to cross, and in that way you can compute the times and everything. And in dimension 3, it's also known, and this was Belarus and Ceph. And the pathwise approach works here. That's nice. So, how much I am with time? 15 minutes. Okay, thank you. So maybe I can show the simulation. I'm not so. So now I go to something which I get lost. No, it was not. It's the simulation. This one, right? No, this so this is just this dynamics running. And runs and runs and runs. This is speeded up, otherwise we would stay here forever, no? And so I mean, run. There are small droplets, but they disappear. Small droplets and disappear. So the field is to favor the white, but I had another video which was more speeded up, so it would take less time, but it didn't work for some reason. So, but it will, you know, it will, it's speeded up enough. Now a droplet came, and things will move much faster. See that I am speeding up less now. So I think it's almost, it's gone to the other side. And it's over. Control it. Yeah. So this is the simulation is a situation with the volume, of course, fixed. So, and the beta is fixed but large, and that's what we are looking something connected with. But the hysteresis loop was not in this situation. The hysteresis loop, the age goes to zero. Age going to zero naturally forces my volume to go to infinite, and the beta is fixed. So it's a different regime that it doesn't fit into Freudian tensor chains, finite chain, or with small transitions. So one needs to do something more refined if one wants. It's the same model, it's the same, but this we are in a regime that is not so the same to. So I cannot say so simple because it took a lot of effort to do that, but it's more involved than that. Because why? The volume has to be large, so it means there is a lot of entropy also that one needs to take into account. It's not only the energy that plays the role, as in that those pictures, that those droplets where you just have to compute something involving the energy. When you have volume is getting large, so you need to involve the entropy too. That means that what comes in is the free energy, which is somehow the relation between the two. So, and there's a fundamental work in this, which is Schoman-Schlossman in 98. They considered infinite volume. They do something else. They do something very deep, but they consider an infinite volume of dynamics. So beta is supercritical. That means you are under the critical temperature. There are two phases, and the age is going to zero. That means the regime of hysteresis. So they start with a measure which is less than mu minus. That means on that side of the hysteresis loop, as we had in the picture, it might negatively magnetize, and they look at times which are very large. In this way, the scale of time, the time they are looking is e to the alpha divided by h. And remember, h is going to zero. So this is again. And alpha is a number, it's fixed. And they show that if alpha, there is a critical alpha, such that if alpha is less than this alpha critical, this expected value will be some CK continuity, but imagine it's close to mu minus with some technical thing, which is very important. But anyway, and if alpha is larger, then it will be close to mu plus. But note, this is a very important result. And they identify this alpha critical. And what is really remarkable, this alpha critical is described by an equilibrium quantity, something which one computes in equilibrium for the Gibbs measure. And that's something specifically given, depends on beta in some way. Okay, this guy here, omega, is called the integrate surface tension of a Wolf shape. I think my time is short. Maybe I will not describe much, but I should give at least two words. What does it mean, this? But what is the first message is that you see there is a huge difference between taking an alpha smaller than alpha critical alpha, because this is e to the alpha h. So you, in this way, you cannot see a transition because your age is going to zero. So e to the alpha age is very, very dramatically. So you cannot. So, but that's a crucial result. And anyway, it is also used for us. So I should say just a word. What does it mean, this surface tension and Wolf shape? So in order not to spend much time, but I say, so you should think the surface tension is just the price to pay, that one pays like a large deviation, to have an interface of mu minus and mu plus. So it in a certain direction. Theta is an angle. And then if you have a region, you can say integrate this function. That means somehow is the price of this region to have a droplet of minus and plus. Minus means mu minus, not really O minus, no? And what's called the Wolf shape is the optimal one. That means the one that minimizes. Okay, so, and there is a particular well-defined set up to dilations, and translation is the same. So there is something. And what is written is, you call the Wolf shape is when you normalize this so that the area is 1. Okay, so there is this theorem is very important in the sense that it goes into the right limit, the right setup, which is when age is going to 0. If one is interested in describing hysteresis, it has to be in this region, which was not the case before. Okay, and then we started asking ourselves, with using all the mathematics they developed in that paper, because it's a really beautiful paper, and it's really well done. And there's a lot of good mathematics in that paper. There's a deep understanding of the process. So can we use all the machinery that we have so far, no, that we have worked here and there in this setup? Huh? And that was something with Alex Godelier, which I already mentioned before, Paolo Milanesi, who was his student from Marseille. Can we give the pathwise description of the transition in the hysteresis loop? So if we want to do that, we realize we need, we cannot do it in infinite volume, because in infinite volume, it's not possible to describe, because a critical droplet appears somewhere, because even if the probability is very small, somewhere it appears. So in order to do it, you need to take the volume going to infinite with H in a proper manner, and the H going to zero, and temperature is fixed. And that's what we do. We take a volume which grows like a volume. I say volume because of my habit, but it's area because we are into the mesh. That goes, so it's like a region of size 1 over H, but it's not a square. We take it as a wolf shape of this area. And so this B is going to be a given number, so large enough, no? In order to contain a critical droplet. I will explain afterwards. And we say we start with everything the outside the boundary condition we fix as a minus, because we want to start with minus. So in the loop, we come from the negative magnetization. And so there is mu minus, which represents the metastable state. That's like in the loop, because now we are going to take an H, which is positive, and we start with something negatively magnetized, and we want to see this transition, okay? So the stable measure is with an H and a positive H, and so this, when H goes to zero, goes to mu plus, that the one with a positive magnetization and H equal to zero, and mu minus is the one with negative. At zero, you have two invariant measures for the process. If there is no H, A equal to zero, phase transition regime, you have two extremal measures. And we want to see if the pathwise approach can be done here. So in order to work with these things, of course, what plays the important role is all these self-avoiding contours on the lattice. But the point is that now it's not good to focus only one droplet, because there will be many droplets, because there is a large volume. And in order to describe where it should have the transition, we just do some simple heuristics first. So what is the free energy? That means the price of a plus phase wolf droplet in which a given area in the C of minus. And we need to compute this because we expect that this has to do with the time to escape, because the time should be 1 over this exponential. So we think we see the following. There is a price that you pay to have an interface. And the price that you pay to have an interface is the W, because the W is the price per unit, times B over H, which is the dimension of length. And there is what you gain because you are having a magnetic field that wants to be in that size. So you gain with H, there is a magnet, and this is the area. So you make the form, the compute, and you see that this has a shape like that. And then you believe that, okay, there is this maximum. So if you are below this, it should shrink, and if you are above this, it should grow. So this gives us the hint of what should be. No? So, and this value, the maximum that you have, is what you compute there, and it's attained at this value. So we need to have our B there larger than this. So droplets is smaller, shrink, droplets bigger, grow. And in that way, we want to know how long does it take to be close to, that means to go to the measure with an H positive, no? And that's something that we would like to compare with the time of Schumann-Schlossner. And we compute this, so that means I'm starting with some sigma, doesn't matter, and I look the first time that I am in a set which has this droplet. And you see that this time is going to be like exponentially large in age, e to the beta a divided by a, by age. Age is small, age is going to 0. And it's interesting to compare this with the one of Schoeman-Schlossman. The one of Schoeman-Schlossman is smaller, it's 1/3 of this. And you see, something's wrong. You are not getting the right time. No, watch out. Because what happens that we have why for Schoeman-Schlossman the time was shorter? Because it was in infinite volume. So it is maybe better for a droplet to come from far away and reach the origin than that if you don't have enough space. So nothing is wrong. It is consistent. Okay, and then what we can prove is a theorem along the way that I mentioned before for this process, in the sense that we can prove if we take beta larger than beta critical, that means subcritical temperature. This size is large enough but fixed, and we start with a measure with the negative magnetization on this side of the hysteresis loop, and then the time to overcome the barrier, let us say, normalized properly goes to an exponential random variable, and there is a scale which is much shorter than that, in which you see thermalization, that the process, average time, empirical process will be very close to mu minus. That's the metastable, because that's the one on the left side of the loop in the picture that I started with. This is going to be very close to this one in this sense, up to t. And this time, the time here converts in law to an exponential. But what is this time? There is a little bit, the time is not just the first time that gets out of R, because now I go back to Leibovitz-Penrose. There is a restricted set, no? Because I'm saying, what is this R here, no? There is so we need to do a little bit of randomization. It is not cheating, but we need to do. So this time, I allow the process to get a little bit outside of R, but what are contours which have all the droplets of plus are not too big. So R is that still the plus phase didn't come. R is the restricted, no? That has to do with the metastable. So in this case, all contours, which are negligible contours we disregard here, can be included in a number of Wolf shapes that the total length is not bigger than B plus over H. So there is a recipe. This is the R. And if we were to have consistent with this is somehow consistent with Leibovitz-Penrose, with the work related to Leibovitz-Penrose approach, but was done by other people, the time would be just exiting from R. It's not quite. We allowed it to exit from R, provided it doesn't go out of this set S, which it doesn't disappear completely. There is always some Wolf shape, doesn't disappear. And we allow it to make some excursions in this set S minus R, but I don't want to be too technical, but it's somehow very close. In spirit, you might think that is the time of going out of R with some little randomization. And that goes to an exponential. This is somehow what was prescribed in the pairwise approach. And the main point of the proof, which involves various tools, is to be able to show that this relaxation process restricted to R is much smaller than TH. But the R is quite big, everything. So it's more involved than just in the Friday and Wenzel regime. And I think I am already out of time. I just want to give some references. So this is the paper that I'm talking about. And so here you find in this paper, there are many references for the current literature. So many of those people I mentioned before, I listed here. And there are two books which are useful for students that want to learn about this stuff, or reference books. The old one by Enzo Oliveira and myself. This is more focused on the final inventor approach, so with large deviations. So it gives a more detailed description of the trajectories. And this one of Bouvier and the Frank den Hollander is much more recent, but it's as they announced, they put in the title, a potential theoretical approach. So when you enter with potential theoretical tools, you have a better description of the time of the transition time. You get less information about the trajectory, and you have more on the time. So the two different ways to see it, and I think I finish here, and thank you very much for this.
Questions, comments?
So the first time to reach, the first time when a macroscopic droplet appears. So can you say about that in terms of the inverse temperature? Like,
yeah. In the case that it's finite volume, that's very simple. Yeah, that's in this paper of Neves and Schumann. This is done very. It's a finite Markov chain, so it's a matter just that this geometry of the energy is not so simple, but it is. It is overall. It's at the end. It's simple, and this has been extended for many other chains. Yeah. Yeah, I didn't list all the papers because there are many. That's why I indicated the books, because that makes me sort of, it would be impossible to list all too many. Yeah.
On that question, when you say finite volume, you mean the volume is fixed, or
yeah, the volume is fixed. I'm saying when I say finite volume, it's fixed.
But I mean, if you let the volume increase.
Yeah, in our case, for these hysteresis, we need to take the volume increase. But metastability, but I need to take it finite change going to infinite with age, because it is a phenomenon of finite. Because if you take it infinite, somewhere already exists. And then what you are going to see is when this droplet comes to the origin. It might be faster than when it. Yeah.
Thanks.
Did they go over time? I always have a problem to control this, to look at the watch when I'm